All right. So, um, as some of you know, I talked earlier about the last class. The technology was a little bit not working, so I'm a little flustered at the beginning of this class, and hopefully things, as long as things go smoothly, I'll be a very happy person. Last day we were looking at, we finished off an example looking at the method of initial rates, and we started looking at integrated rate laws. What we are going to do today is we're going to take integrated rate laws and finish it, and then look at an example of that. Once I have done the example on method of this integrated rate laws and applying them to determining the reaction order, then we are done the material for problem set 1. We probably won't be done that until Wednesday, but you should have, by the end of today's class, sufficient knowledge to do the vast majority, if not all, of problem set 1. With regard to the quiz, since it's a question I keep getting asked, once I sit there and go, okay, that's it, we're done the material for problem set 1, which will be Wednesday, the quiz will be 5 or so days after that. So I will probably open up the quiz for problem set 1 next Monday to Wednesday. So you'll have any time in that Monday to Wednesday to do the problem set 1 quiz. It'll give you 3 days to do it. So hopefully that answers the questions that I've been receiving about how do the quizzes work and all the rest of the stuff. With regards to the material that we have covered, method of initial rates and the start to integrated rate laws, I'm not going to do questions off of the problem set, but if anyone has any questions about the material that I presented in class, I will endeavor to clarify your understanding. Give you a few seconds to think about that. Any questions? All right, seeing no questions, what we're going to do is just remind you where we were at last day, and, excuse me, that should work, good. So we were looking at the integrated rate equations, and we looked at a 0th order reaction, in which case you had change in concentration over change in time, was not dependent on any concentration, and we had a differential rate equation. We integrated that rate equation, and I'll show you that equation in a second, and we calculated the half-life for a 0th order reaction. And that information is presented here. The integrated rate equation for a 0th order reaction is concentration as a function of time is minus kT plus the initial concentration. So it's linear in concentration. So you can see the concentration starts off at A0 and it goes down linearly to 0. The slope of that line is negative K. It is the rate constant itself, or negative of the rate constant itself. The half-life is A0 over 2K, and you can see that the half-life gets shorter and shorter as the initial concentration gets smaller and smaller. So that's what we have for a 0th order reaction. We had a number of examples. Basically, they deal with catalysis. The degradation of alcohol by the liver is a catalytic process, enzymatic process in the body, but it is still a catalytic controlled process. Reactions involving solids and liquids, doesn't matter how much solid and liquid is there, as long as it is present, it will react. Are examples of 0th order reactions. Then we looked at 1st order reactions, in which case there is a concentration dependence to the power of 1, as we saw here in the differential rate equation, delta A over delta T is minus K times A. We integrated it, we determined the half-life of that reaction, and we didn't look at this profile yet. I'm going to get to that in just a few seconds. I want to look at this. This was the equation we had for an integrated rate equation. Natural log of A, function of time, minus kT plus the initial concentration. That was one form of the integrated rate equation. We did come up with a second one, realizing that if this is a natural log form, there should be an exponential form as well. So did a little bit of math here, reminded yourself of the math of logs, and we came up with an exponential form of the 1st order rate equation. Concentration as a function of time is is initial concentration times e to the minus kt. So that is the equation, the two equations that represent the integrated rate equation for a first order reaction. And just to finish that off, this is what the profile looks like for a first order reaction. Now, just the big figure here plots concentration versus time. And it's not linear. Concentration versus time drops down. It's actually an exponential decay. Nature of the logarithm operation. It's an exponential decay. However, the inset shows the natural log of concentration versus time, and that is the linear function. So natural log of concentration versus time is linear, and the slope of that line is again minus k. So if you want to calculate the rate constant, you just need to find the slope of the line. The half-life, did we calculate the half-life? I don't think we did. I know we didn't do it. So we need to go through and calculate the half-life for a first order reaction. You've seen the figure. Let's go through and do that. Good. So this is the half-life. So I'm going to start with the exponential form. Concentration as a function of time is initial concentration e to the minus kt. And the methodology is exactly like what we did for a zeroth order reaction, and it's exactly what we're going to do for a second order reaction. At the half-life, two things are happening. The concentration as a function of time is half the initial concentration. And we're going to have a units change. T goes to T 1/2. Take that, substitute them in up there. And what we end up getting is that expression right there. What we see is that A naught cancels out, and we're left with 1/2 is e to the minus kt 1/2. To deal with that, we're going to take the natural log of everything. And so that gives us natural log of 1/2 is equal to minus kt 1/2. Okay. Just a reminder about natural logs. How can I simplify the natural log of 1 over a? How does that simplify to? What does that simplify to? Either audio or in the chat. Anyone want to offer me that? Natural log of 1 minus natural log of a. Yep, that's correct. But that can be simplified even further. What is the natural log of 1? That's correct. Natural log of 1 is actually 0. So this simplifies to negative the natural log of a. So that means this expression becomes negative the natural log of 2 is equal to minus kt 1/2. And that leads to the expression t 1/2 is equal to natural log of 2 over k. So that is the half-life expression for a first-order reaction. Oh, so much for a green screen. Oh well, not much I can do about it right now. And so that half-life equation gives you T1/2 ln 2 over K. It's independent of concentration. That is a key important factor for first-order reactions. The half-life is independent of concentration. So the half-life is constant, as you can see across the bottom, to go from the full A0 to half to a quarter to an eighth. You get exactly the same value every time. Whatever. So what are some examples of first-order reactions? So if you think back to your childhood, or maybe your bedroom today, that's okay. You may have gotten stars, or could be characters or dinosaurs or something like that, that you put on the wall of your bedroom. And those stars, when the lights are on, end up absorbing the higher energy blue and ultraviolet light and storing it within the molecules in the stars themselves, and within molecules in the stars themselves. The chemical that stores it is actually called the phosphor. Then when you shut off the light, these stars glowed for a period of time, and they slowly faded away after, give or take, 45 minutes, an hour. That decay of intensity of light follows a first-order process. So that emission of radiation from an excited state, phosphorescence in this case, those stars, is a first-order process. Radioactive decay does the exact same thing. The dissociation of an acid. You throw concentrated acid in water and it dissociates. That dissociation is a first-order process. And what's also presented there is what's called the gas shift reaction. And the gas shift reaction is the reaction of carbon, reacting carbon, solid carbon, with water vapor at elevated temperatures, ends up giving you hydrogen gas and carbon monoxide. Carbon is a solid. It is 0th order in carbon. As long as carbon is present, life's great. It is first order in water. And so the pressure or the concentration of water vapor is first order for that gas shift reaction. Some examples of a first order reaction. Does anyone have any questions on that? We're all good? All right. Now let's look at a second order reaction. There are two versions of a second order reaction. The first looks at one entity being raised to the power of 2, Ka squared. The other looks at two reactants being raised to first order, Ka and B, each raised to the power of 1, first order in each of those. We're going to focus on the first one. The second one is looked at in your textbook, but not something that we're going to be expecting you to be able to do in class. So the first one is easier to come up with integrated rate equation. So we're not actually going to derive the integrated rate equation. I'm going to give it to you. But we are going to derive the half-life, because that is something that I fully expect you to be able to do. So when we have a second order reaction, with a second order reaction, the differential rate equation that we're working with is delta A over delta T is equal to minus Ka, the second order power. That is the differential rate equation. The integrated version of that is 1 over the concentration is equal to kT plus 1 over the initial concentration. If you are taking calculus, on you to go through and do that, and that is the integrated rate equation. This, by the way, is also in a linear form, y, mx, and b. So plotting 1 over concentration versus time is linear. So that is the integrated rate equation. In order to figure out what the half-life is, for a second order reaction, we're going to take that integrated rate equation and exactly like what we did before, at the half-life, comma, we're going to let A as a function of t is a 0 over 2, and t goes to t 1/2. Those are going to get substituted in to that equation. And what you end up with is 2 over the initial concentration is equal to kT 1/2 plus 1 over the initial concentration. Moving that over to the other side, you end up getting kT 1/2 is equal to 1 over the initial concentration, which rearranges to give you T 1/2 is equal to 1 over K times E0. And I fully expect you to be able to take an integrated rate equation, any integrated rate equation, and determine the half-life for that. As a matter of fact, that's one of the questions on the problem set. So that is how we get the half-life equation, and that is the half-life for a second order reaction. So what does the reaction profile look like for a second order reaction? It's presented here. Just plotting concentration versus time is a nonlinear function, okay? Concentration versus time gives you a curve. It's actually an inverse curve, 1 over x. But if we were to plot 1 over the concentration versus time, that's what's in the little inset on the right-hand side. 1 over the concentration versus time is a straight line relationship, and the slope is now the rate constant, K. In the case of second order reaction, the half-life keeps getting bigger. So it's a faster reaction to start with, so a short half-life to go down to a quarter or to a half, then longer to get to a quarter, longer to get to an eighth, and so on and so forth. So we have different observations as to how the half-life goes for a 0th, first, and second order process. Some of the examples associated with second order reactions generally involves 2 reactants doing something. Dimerization is a very common reaction. The nitrogen monoxide reacting to form the NO dimer occurs in the atmosphere or stratosphere as part of ozone depletion reactions. It's the, and the word escapes me. Anyway, it's where they storage of nitrogen monoxide dimers. Anyway. In aqueous solution, many carboxylic acids, they fit actually really well together, they fit together, and they are actually able to form a dimer of carboxylic acids. And I just showed the idea of formic acid coming together, hydrogen bonding between two formic acid dimers to give you, between two formic acid molecules to give you a dimer, is another example of a second order reaction. So this is a summary of the analytical rate equations that we looked at. We looked at zeroth, first, and second order. Given the differential rate equation and given the integrated rate equation, I'm not expecting you to be able to convert between the two. This is what you have here. And for the first order one, there's multiple versions. You have the natural log form, which is presented here. There's also the exponential form. You have the half-life equation for each of those. And what is linear? Concentration versus time for a zeroth order, natural log of concentration versus time for a first order, and 1 over concentration versus time for a second order reaction. So let's look at one way in which this can be applied. This is an example. Sugar, common table sugar is sucrose, which is a disaccharide. And when you put the disaccharide in water, it hydrolyzes to glucose and fructose. So glucose and fructose are monosaccharides. And that process is first order in sucrose. The half-life at room temperature, well, 25 degrees, is 8.4 hours. And while water needs to be present, it is zeroth order in water. The water is a liquid, the solvent. So here we have sucrose plus water reacts to form glucose and fructose. And you start off with a sugar drink containing about 0.3 moles per liter of sucrose. What is the sucrose concentration remaining after 24 hours? That's what we're asked to calculate here. So you are told that this is a first order process. So the equation that you're working with is that of concentration as a function of time is equal to the initial concentration, e to the minus kt. To make my life easy, I'm going to say that A is sucrose. Rather than writing sucrose out or using the chemical formula, A is sucrose. And the initial concentration of sucrose is 0.30 moles per liter. We don't have a rate constant. We have, whoops, that's not what I want to do. That's not what I want to do. Hold on. I need to figure out how I got into this mode so I can get out of it. I have no idea how I got into this mode. Good. How do I get out of it? Lovely. Time out while I figure out what I just did. Okay, copy to clipboard. Am I back to working? Yes, I am. I'll figure out what I did eventually. Sorry, so we were there with KAT. We don't have K, but we have a relationship that relates K with the half-life. And since this is a first order reaction, we know that T1/2 is equal to natural log of 2 over K, and that's equal to 8.4 hours. So K is equal to natural log of 2 over 8.4 hours, which is 0.0825, 1 over hours. That underlined 5 indicates that it's not significant, but I'm carrying it through my calculations anyways. Give me a second here. That should make life easier for everybody to see what's going on. Okay, so now I'm going to take this information and that and substitute everything back into that original equation. And what we're left with is that concentration at time t, which is going to be 24 hours, is 0.30 moles per liter, E negative 0.0825, all right, the units of hours cancels, and which makes my exponent unitless, which is kind of what it needs to be. And when you do the mathematics, what you get is 0.0414 moles per liter. And that 4 is not significant either. I'm limited to 2 significant digits. So 0.041 moles per liter is the concentration after 24 hours. Does anyone have any questions on that? Okay. All right, so that is one example. We're going to look at a different example in a few seconds, but it does bring up a little story that's associated with this question right here. When I was a kid, Kool-Aid was something that was around and available in the house, and I at one point in time made the comment that the stuff that we just made tasted a lot different than the stuff that was made a few days ago. And my mother kind of looked at me like I was crazy, and I just accepted that fact that I was crazy. But then I went to university and learned about the hydrolysis of sucrose, that sucrose hydrolyzes to glucose and fructose. You know, at room temperature, it's 8 hours. In the fridge, it'll be a couple of days. But after a couple of days, the original drink that you have actually doesn't have any sucrose in it anymore. It has glucose and fructose. And yes, glucose and fructose actually taste different than sucrose. So while my mother thought I was crazy for thinking that the drink tasted differently after a few days, I was actually right, and I had made an observation. I just didn't know what I was making. I did end up getting a degree in sciences, so crazy is not that far off in terms of my mental state, but not for that reason anyway. Does anyone have any questions on this example? The calculation or story or something like that? Everyone's good? Was it the Kool-Aid that inspired me to get a doctorate in chemistry? Actually, no, it was my second year chem prof. My second year chem prof versus my second year physics prof. The physics professor talked to the board. The chemistry prof did demos and bounced around the board and was really energetic, and that was a lot of fun. So as I was balancing chemistry, physics, physics, chemistry, the chem prof absolutely, led me in the direction of blowing things up, and haven't looked back since. Usually because the police are behind me wanting to ask questions about something that just went boom. But hey, whatever. All right, let's continue. So how do we determine reaction orders using these integrated rates? And it simply comes down to the fact that they have different linear relationships. And so the way we determine the reaction order is we literally take our data and we plot concentration versus time. Is it linear or no? Yes or no? If it is, it's a zeroth order reaction. If it's not linear, It's not. Is the natural log of concentration versus time linear? If it is, then you have a first order reaction. If it's not first order. Is 1 over concentration versus time linear? Yes, second order. No, not second order. We are ultimately limited to the orders that we are testing by plotting. It's not going to find a 0.5 or a 1.5 relationship because we don't test for that. But 0th, first, and second order reactions are the most common, and thus things that we can test for quite, get the vast majority of reactions based on this type of testing. So this is the data that we're going to be working with. This is the decomposition of dinitrogen pentoxide at 365 Kelvin. And what was monitored was the partial pressure of N2O5 as a function of time. So there is a similar problem to this in your problem set 1. You can work in pressure. Working in pressure is fine. Pressure and concentration are related. Or you can convert to concentration. Completely up to you. You're going to get the same answer. Because I want to remind you of the relationship between pressure and concentration, I'm actually going to convert to concentration here, but you don't need to if you don't want to. Like I said, working in pressure units is perfectly fine. So I am going to need to create a data table. There's a lot of data that's needed for this. And so just to put things in here, make my table, I have time. And we're going to have pressure of N2O5. We're going to have concentration of N2O5. We're going to have the natural log of the N2O5 concentration. And we're going to have 1 over the N2O5 concentration. In terms of units, just because I don't have a lot of space, this is going to be in seconds. This is going to be in bar. Concentration is going to be in moles per liter. Natural log of concentration doesn't have units, and this is going to be in units of liters per mole. We're going to look at data for 0, not every one of them. Again, time and calculations, 20, 40, 60, and 70 seconds. So just off the table that was on the previous page, this is 0.992 bar, 0.289. There. All right, so that's the data we've given. Now we need to calculate the concentration, natural log, and 1 over. In order to do that, just remember the relationship comes from the ideal gas law. PV equals nRT. Well, concentration is simply N over V is P over RT. And that is concentration. By definition, N is in moles, V is in liters, N over V, concentration, P over RT. So to apply this to 0.992 bar, I have N over V is equal to and the appropriate value of R that cancels out with bar is 0.08314 liters bar per mole Kelvin, and we're working at 365 Kelvin. In terms of units, bars cancel, kelvins cancel, and we are left with units of moles per liter, and this is equal to 0.0327 moles per liter. I'm going to substitute that back up here. and we have 0.0327. The natural log of that number is negative 3.420. And 1 over that value is 30.6. And I'm just going to fill in the table with the rest of the data values. All right, so that is the completed data table that we have. What are we doing for time? 8 minutes. Okay, what I'm going to do is I'm going to start the graphing process to test for the different orders of reaction. Kind of hoping I have a little bit more space here. There I do, apparently. All right, so we are going to do a 0th order test. And in that 0th order test, I'm going to be plotting concentration versus time. So this is concentration versus time in seconds. And 0. $20, $40, $60, $80. We only need to go to 70, but we're good. So the concentration, 0.02, 0.04 is all we need. And, excuse me, then to look at my data set, at time 0, we have 0.327. 327 is about right there. At 20 seconds, it is 0.00952. Right there. 0027 at 40 seconds. At 60, it's 0.00076. And 70, it's slightly less than that. This figure definitely doesn't look linear, but it fits pretty good a profile that goes like that. So because we do not have a linear relationship, it is not a 0th order function. I also want to point out at this stage that I do expect you to be able to graph these things by hand. As a matter of fact, if you look at the sample exams online, there will be, either on the term exam or the final exam, there will be graph paper given to you and the expectation that you create graphs to determine the order of reaction. In first year, I want to know that you are able to create a graph by hand. if you when you continue on and take analytical chemistry in second year or higher level courses, sure, then we're going to use Excel. But you need to be able to create a graph by hand in order to create a good quality graph in Excel. And getting you to do it on an exam is one way of assessing that. So, but what we have here is that it's definitely not a 0th order reaction. This is where we stopped in the last class, and I want to keep the 2 classes at the same location. So we're going to call it for this class, and I will have some time to answer your questions. So please feel free if you have any questions on this material or on anything that we've covered thus far. So I do have a question for you. I'm actually going to turn off the recording